Okay, so let's start. Okay, so as you see, empty blackboard, which I think is a good idea for this subject, because if you go too fast, too many equations, and it gets too complicated. So let's start from where I stopped last time with these moments, and then since people are already anticipating, I was just, so where's the Navier-Stokes equations? Okay, so today, let's see, without going too fast, how the classical equations come up. So let's let's make some orientation. So remember, I won't write the moments yet. So let's remember the notation was this was called F. Etc. Dot, 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 dot. You can figure it out for yourself. So that was the notation relating the moments to these capital F's. Okay. Now let's give some continuum mechanics names to these things. Well, the first two are easy, and the third one is not easy. Okay. So the first one says, okay, you're adding up over all possible velocities the density of finding a particle at each velocity. So if you add them all up, you should get something like the density. Let's assume the molecules have mass 1, so we won't worry about keeping track of it. So this one we can also think of as the density rho. Now we've integrated out, the size, so it only depends on space and time. Okay, the next one, well, that also makes sense. It's velocity times mass. Velocity times mass we usually think of as momentum. So we would write this as rho. I'll leave out the xt now that everybody depends. We've integrated. So and I'll use the letter I, v sub I. Okay. And that equals rho v sub I. And we already defined rho upstairs, so that defines v sub I. So each one, it's canonical. So I use the information from the third one. Okay, the next one, I'll define, now this, I said it gets a little trickier. So Fij, okay, so that one I write as minus Tij plus rho vi vj. And I was asked about this one, so okay, that one also makes sense because these two, the rho's and the v's, were defined on the previous level, so really this is just a definition of the Tij, the stress tensor. Okay, and we can continue, but let's just do one more. Okay. And two more. So the next one is is taking the trace here. So that's 1/2 Fii divided by rho minus 1. Let's do it reverse. Let's take the trace here. So the trace is Fii, right? Which is minus Tii plus rho v squared. Okay, but and T was defined upstairs. So this defines what? Well, so far I didn't do anything, but let's define epsilon as 1/2 Fii minus 1/2 v squared. Okay, so what is this? It says that the quantity, I'm giving a special preference to the trace, and it's 1/2 Fii minus 1/2 v squared, and epsilon will come to be the internal energy, which in everyday life is some multiple of the temperature. So, and one more guy, which is the Fiik, And it's here, okay, 1/2 FIIK. I put it as 1/2 equals QK minus rho epsilon 1/2 rho V squared VK plus TIK VI. Okay, so what's new here? At this level, we had incorporated the K's. So it's 3 pieces of information, and really that's what comes in the Q's. So what are the Q's? The Q's are the heat flux. So if I move this around, of course, this just defines QK in terms of the FIIK. Okay, one other piece, I'll plug it into the equations and it should look familiar in a second. But one other piece of useful fact is let's decompose. Now you see why I didn't put it all on a slide or something. It goes too fast. Okay, so let's decompose Tij. This is as complicated as it gets. So let's decompose the Tij into 2 pieces. Right, decompose. Tij, if you want to think in terms of matrices, the T is some multiple of the identity matrix plus a leftover piece. And we make the leftover piece such that its trace, sigma ii, is identically equal to 0. So it has a traceless part, and all the trace information is here. Okay, that says Tii, of course. Sorry, what does that imply? It says Tii is minus 3p, just taking the trace. So Tii is minus 3p. Okay, that's very nice. So what do we have here? So we have that Tii is minus 3p. Let's go back to the definition of epsilon. So that says epsilon is 1/2 FII. Okay, what is FII? It's minus TII, and TIA was minus 3p. Minus times minus is plus, so this is 3p. If I don't make a mistake. Plus 1/2 rho V squared. Okay, but I had to do FII. That was the, let's make sure. So then I had to, so this was, and now I have to subtract off 1/2 rho V squared. So, okay. Well, of course, it's rigged up to have perfect cancellation. The inventors of mechanics knew what they were doing. So we have, and I left off anything? 3p. Why did I? FII was minus, oh, it was plus 1, right, let's see. FII, let's see, it's 1/2 E epsilon is 1/2 FII, so let's track. Right? And TII was minus 3p. Right? So that becomes plus 3p over 2. Then I had plus 1/2 rho V squared. So that took care of putting in all the information from there. And then I subtract off the 1/2 rho V squared, and they cancel. So epsilon is 3/2.
Isn't it just a V squared, not a rho V squared?
Say that again?
The definition of the epsilon, I don't see any rho.
Let's.
I think you dropped the road.
I lost the row someplace. Where did I drop?
Internal energy.
The epsilon. Oh, it should have been divided by rho. That was the mistake. So epsilon should have been so epsilon is defined as 1/2 FII minus divided by rho minus 1/2 rho v squared. Okay, now it comes out to the ideal gas law. So now let's plug it in. So FII divided by rho. Okay, so no rho here. Let's do it again. Okay, so make sure. So FII divided by rho. Okay, now it's better. So FII divided by rho is TII divided by rho, so it's 3/2 over rho. And here no rho, because I subtract off the 1/2 v squared. Okay, that's the advantage of doing it slowly. So what did we find? So we found that epsilon times rho is 3p. So 2 rho epsilon equals 3p. Or p equals 2/3 rho epsilon. So if we think of epsilon being related to temperature, it says the pressure is proportional to the density times the temperature, which most people learn in high school as some law, PV equals nRT, okay, which everybody learned in high school for the ideal gas law. So we've re-derived that the formulation, just by taking moments, if you're clever, you can re-derive the ideal gas law, which makes us very confident. Of course, all these ideas were known to Maxwell. That's why he was so happy with this approach of doing the equilibrium theory. It was Boltzmann who put in the dynamics. Okay, now let's write down the equations. Okay, so we're going to plug all these moments in. Let's review just to take the first 5 moments. So remember, it's d dt of f, d dt fi, d dt fi plus d dj fij, and d dt of just a trace plus d dk, fi ik equals 0. So remember, those were the first 5 moments. So this was one equation. 1, 3, 1. So 5 equations. And now let's plug in. So the first ones are easy. Let's all do it over. Let's see, I'll just do it underneath. I might have to write. So the first one is easy. So let's do the first one here. Okay. So the first one is d dt. Should look familiar. So f was rho. And this is d di of fi. And fi is rho vi. Okay, so this is sometimes called the continuity equation or just conservation of mass. Okay, the second one, of course, it has this structure, so it's d dt of rho vi, and then it has to be d dj of fij, and fij, well, let's do it first. First, it was rho vi vj. That part is easy. Minus rho plus rho vi vj, and now minus tij. But tij is minus p delta ij, so on a minus times a minus is a plus. So it's plus p delta ij, and then a minus sigma ij, and we set that equal to 0. So I did those two. And this, of course, is the rate of change of momentum, so that's conservation of momentum. Linear momentum. Now the last one is a little messier. What can I do? Okay, so it's one equation. So it's d dt of fii. Fii was here. So fii was, let me make sure I get it right. So yeah, the first part is easy and the second part is a mess. So the fii is easy. FII is rho e plus this other stuff. So let's plug that in. So it's 2 rho epsilon rho v squared, and then all those leftover terms. ddk, and it's minus 2, let's say tki. Well, I'll clean that up in a second. Vi plus 2 rho epsilon plus rho v squared vk equals 0. And then the 2, it is missing a 2 qk. Let's move that to the other side. Okay, now the only one I can clean up easily is the tki. So let's move the tki to the other piece. So tki, we'll plug in the definition, and this will make it, we write the t using the decomposition, and then move the extra term over. So let's see if I can do that without making any big mistakes. So let's divide by 2 here. Okay, and then I'm going to substitute. And this will give me tki, I'll get the pressure minus P delta ij ddk, I hope I have that right. Something is ddk, dd delta ik probably should be. And then it gives us another term over here, ddk sigma ik vi. Okay, so I was afraid, so this is conservation of energy. So the first two are easy, and the third one, well, it wasn't hard to get, it's just a little keeping track of things. Okay, so there we are, and we had the ideal gas law. The P equals 2/3 rho E. So we know everything. So how many equations do we have and how many unknowns? Well, let's keep track. So we had, as before, 5 equations. Can't do anything about that. But many, too many unknowns. So let's see. So of course we had the unknowns rho, Vi, epsilon. Okay. So that would be fine, and that would take care of all these terms, but then there's some leftover terms. For example, the ddj sigma ij. So if we move that to the right-hand side, let's do that. Okay. And what else do we have? So we have to have the sigma ij's. And then unfortunately we also have, we have the q's. Okay, so how many sigma ij's are there? Well, it's symmetric, so it should be 6. But the trace is 0, so only 5. So this is 5 more guys, plus 3 more guys. So it's the original 5, plus, so it's 13 unknowns. So unfortunately, 13 unknowns and 5 equations. Okay, that's the way life works. We can't do much about it. So now let's think, as I said, okay, I don't know how to solve that system. What's the simplest truncation? Simplest truncation is set the rest of the leftover unknowns equal to 0. So set these guys equal to 0. Okay, why not? Well, what does that leave? That yields 5 equations So if we do that, then the 13 unknowns become 5 unknowns. And we have 5 equations and 5 unknowns, and that's just the Euler equations. So we see that the Euler equations, as given in the continuum mechanics books, okay, they're just derived by some postulates. And the continuum mechanics person would say, I'll tell you from experiment, from wishing, from talking to my wife. My wife said that P equals 2/3 rho E, rho epsilon. Okay, that's one way to do it. And my wife also told me that, what was the other one? So that gave us the pressure. In fact, that's all we need in there. Okay, we close the system. Okay, so my wife tells me, and okay, so one way to do it in continuum mechanics is you just make up a rule. And that's what continuum mechanics is based on. There are balance laws, and then there are rules. And the rules are called constitutive equations. Statistical mechanics is different. No rules. I don't have to ask my wife, at least about this thing. Okay? All I have to do is do the balance and chop off what I don't like, and I have no rules. The statistical mechanics takes care of the rules automatically. So it's rather powerful. Okay? So it eliminates the need for making rules or constitutive equations. Okay, so we had the Euler equations. Now I was asked...
I have one question.
Yeah.
If those two does not agree,
Yeah.
then which one will you believe?
I believe statistical mechanics, but I always will listen to my wife. So, then the next thing is, and I was asked it last time, okay, what's another way to closure? In continuum mechanics, we'd say, okay, we threw away these terms. Maybe you don't want to throw away those terms. But if you're not going to throw away those terms, then you have to make them to be functions of the terms you have. That is, these guys have to be functions of these guys. Again, in continuum mechanics, it's just asking somebody. You ask the engineer, you ask the physicist, you do an experiment, but it's not self-contained, okay, right now. Okay. What's the common assumption? Common assumption is that sigma will be a gradient of the velocity, and Q might be a gradient of the internal energy, which is temperature. If you do that, that's continuum mechanics, again, and a closure rule not from the moments, okay, then we'll get the so-called compressible Navier-Stokes equations. They're actually Navier-Stokes Fourier, because it has also Fourier's law of heat conduction is incorporated. But that's, if this is to be a self-consistent theory, we shouldn't have to do that. So there should be a way of getting the Navier-Stokes and Fourier directly, because we don't want to have to do the continuum mechanical story. So the next thing is, how do we do that? Okay, so let me make sure I didn't leave anything out, so give me 2 seconds, and I think we're up to the... So that derived the Euler equations. Okay. Okay, one other remark, which I see, it's here, that's not crucial. Okay. If we wanted to do closure without, here I had 13 equations. Okay. The first level of closure was just to set these guys equal to 0. Okay. Let's imagine, which I won't write it all down, you continue the process. Keep taking moments, and again, you'll always have to do closure. Now, there's 2 possibilities. Okay. Let's say I did more moments. What's the possibility? There are leftover guys. Okay. And one possibility, just assume the leftover guys are linear combinations of the original guys, the original unknowns. In fact, that's all grad did. So you can choose the grad closure is the additional moments, are a linear combination of the earlier moments. Okay. But the grad closure, okay, it's nice, but it has a flaw. And let me mention the other rule. However, the good news is from the example I'm going to do, they both give the same answer. Okay. But there's another closure, which was Muller and Ruggieri. Okay. And it makes sense historically if we think about it. Okay. Muller and Ruggieri said, okay, we'll make a closure, but we'll make a closure such that it has to be consistent with the second law of thermodynamics. So what's the Muller and Ruggieri theory? It says when you do the closure, whatever it is, it has to be such that there'll be two functions, and I'll use eta, or how about phi and psi? That's, I think, how in the Fermos's book. So that there are two functions, phi, which depends on all your unknowns. So you've done the closure, and you have two functions, phi, which depends on all the unknowns, and psi, which depends on the other unknowns. So it's the ddt of phi plus the divergence of the vector psi is less than or equal to 0. In the language of PDE, this means you're enforcing an entropy inequality. So one way is just to do linear combinations. Another way is to enforce an entropy inequality. If you can do it and still make phi convex. Okay. What's the advantage of this one? Now, this was 1949 and this is 1980s. So, of course, there's a big difference. So 1949 and about 1980, I didn't, plus or minus. Okay, so this is 30 years later. Okay. So, of course, the first guy through always has the harder job. The second guy through can think about what went wrong. What went wrong with Grad's closure? Well, Grad was a smart guy. The Grad closure, when you do it, the equations that you write down may not be hyperbolic. It's a system of conservation laws, but they may not be hyperbolic. That's not very nice, because it means the initial value problem isn't even locally well posed in the bad region where the equations will be elliptic. So the Grad closure, while appealing, is simple, okay? But you can have loss of hyperbolicity. The Muller-Ruggieri theory rigs up hyperbolicity because it's a theorem of Friedrichs and Goodenough that says if you can find such a phi, that means the system could be made symmetric hyperbolic. Now the point is, historically, is that Friedrichs, Goodenough, I'm sorry for the sloppy writing, but you got that, I think, was about 1960. So it makes sense. How could Grad have known this if the theorem wasn't proven till 10 years? I mean, he was smart, but not that smart. He couldn't predict the future. So it makes sense that these guys had the advantage of knowing the Friedrichs, Grad, Lax was involved, Goodenough. Friedrichs Goodenough theory, and Lax's name is also on one of the papers. Okay, so they had the advantage of knowing what they were looking for. But as I said, when I do the example, and it's, okay, I worked it out, that at the range, in the level of this computation that I'll do, they're the same. So it makes no difference. That is, if you linearize, at the level of linear theory, the two are identical. At the level of nonlinear theory, okay, they're not identical. But when you linearize around the rest state, it's the same. So it's a technical point, but not crucial. That's not the reason for why I claim Hilbert's the reason I claim for Hilbert's program failing is much simpler than that. Okay. It's not a technicality of nonlinearity or anything like that. Okay, so I mentioned that. So now let's go back and see. Okay, so let's leave this up. I think I'll leave the equations up for a moment, but I'll erase over here. So let's go back to the Boltzmann equation. And get back to the theme of the lectures. So there's our friend Boltzmann. Okay, and we're interested on, that's things at the particle level, and we're interested in how things proceed at the continuum level, trying to get from one to the other. And that requires a simple rescaling. Rescale. So I'm going to rescale space and time. So wherever I see a t, I'll put t prime, okay, and then divide it by epsilon. Wherever I see an x, I'll put an x prime and divide it by epsilon. So that means is the new variable t prime, say, goes between 0 and 1. The old variable goes between 0 and infinity. And the x prime, if we want to say between 0 and 1 in one dimension, okay, then the x would go between 0 and infinity. That means I'm looking at things on a very large scale now, which is where the continuum mechanics takes place. Now I have the advantage of having the chalk. So when I make that substitution, right, I get that. Let's write it as dd psi, like that. ddx psi. F, sorry. So when I put in xi equal to x prime, I get xi prime and then an epsilon like that. Okay, now I can hardly resist not to move the epsilon upstairs. So multiply top and bottom by epsilon, and I get that. And if I then can't resist not to divide by epsilon, you see I've taken the original Boltzmann equation and rescaled it such that I put an epsilon underneath the q. So let's rewrite the left-hand side and figure. So after I did the rescaling, the equation looks like this, where the t and the x, in fact, are the new ones, but I don't want to worry about the prime each time I write it. So that means on the macroscopic scale, the equation looks like this. Okay, that's the first one. So the epsilon is called the Knudsen number. Okay, which is a measure of the mean free path between collisions. Okay, but it's not important. For us, it's just the rescaling. Okay, now let's get back to the story with Hilbert.
If we do the rescaling x, how about the cosine?
What?
Velocity.
No, we only rescale the space, not the velocity. Because velocity is going to be averaged out, and also velocities go from minus, we integrate over all velocities from minus infinity to plus infinity, so. Speaking of that, if you think about it, okay, what's sort of fake in this version of the Boltzmann equation? Okay, velocities can go infinitely fast. Now, particles in real life cannot go infinitely fast. So if in the process, when one does this and develops a theory where the theory has some parabolic part, where information can be propagated infinitely fast, there is no contradiction, because it was built into the original theory that things can be propagated infinitely fast. Okay, but let's go back to Hilbert. Needless to say, if Hilbert postulated this question, he must have tried to solve it for himself. Yeah, so Hilbert himself tried this. And what did Hilbert do? Hilbert said, oh, I see a small parameter epsilon. Let me try a matched asymptotic expansion. So Hilbert thought, okay, let's try to write it's psi x t, and we'll write it in the following form. Plus dot dot dot, and this is course called the Hilbert expansion. Okay, well, let's plug in the first term, because that's the only one we can do easily. So if we plug this in, what do we see? On the left-hand side, we see df0 plus dot, okay? And what do we see on the right-hand side? We see q of f0 divided by epsilon. So let's just write down the first one. So if I plug in to leading order, I see this one plus dot dot dot, and this one I see q of f0 plus epsilon f1, etc. Like that, right? Okay, not very deep. Multiply both sides by epsilon. Okay, let epsilon go to 0, and we see that the left-hand side, if everything was nice, we would get 0, and on the right-hand side, if everything is nice, we get q of f0. So we at least know the first term in the expansion. So the first term in the expansion is the solution to the equation q of f0 equals 0. But I told you, there are only two places where we use the form of the collision operator. The rest of the stuff, all that technical stuff, is irrelevant. All we needed to know was the collision invariance and what the solution of q of f0 equals. And the q of f0 we said was equal to, if I have to, psi x t. Okay, so now notice q of f0, the f0 could depend on x and t. That means those coefficients a, b, c, whatever, could depend on x, t. But remember, the crucial part was there was some number here, v, which now could depend on x and t, minus psi squared. And then there was some constant here and a constant there. So let me go look up the constants, which actually can depend on x and t. So I'll get it here. Put on my glasses. So it's here in the front, it's 2 pi r theta, which can depend on x and t. Theta is the temperature. And here is divided by 2 pi r theta x of t. And minus 3/2, e to the minus, I think that's right. Okay. Okay, now I didn't define theta, so let me tell you the theta. So that's rho epsilon equals 3/2. Remember, it was rho. So this is the E, right? Remember, rho epsilon was related. Rho epsilon was related to the pressure. Okay, so if you put in the pressure was 3/2. Was it 3/2? I have the 3/2, right? So rho is 3/2. So the pressure is here. So just another way of doing the definitions. Okay, but of course that's the ideal gas law. No surprise. Okay, so what's the point? Okay, so the constants aren't important. Of course, this is the Maxwellian distribution. So let's see it. So it's F0, a temperature downstairs divided to the raised to the 3/2 power, and then this exponential upstairs. Okay, so that's the Maxwellian distribution. Oh, by the way, how did I know how to get those constants? Why is it that way? And the answer is simple, because if I plugged in F0, right, it has to match up. So if I plugged in, to find out the constants, I plug in the F0, which had the A, B, C, whatever it was. I plug in the F0, it tells me this one has to be this one has to be this one, and this one had to match up with the pressure. And that's how you get it. It's not made up. It's just balancing the moments. Okay, that's very nice. So what does it say? So we know F0. So we know to leading order F0. Okay. Okay, now let's do the same scaling on the balance laws. So it's easy to do. If I do the same scaling on the balance laws, it's easy. I change t to t prime over epsilon, x to x prime over epsilon. Here the perfect balance. So nothing changes. I change t to t prime over epsilon. Okay. Here t to t prime over epsilon. Okay. Now here, okay, I have this guy left over. Perfect balance. Let's see. So ddj of sigma. And here t to t prime over epsilon, here to t prime over epsilon, perfect balance. Okay, so what do we get from plugging in? Okay, if we plug into first order, okay, we get, again, conservation laws of mass, momentum, energy, where we're using the F0 has been plugged into the capital F. Okay. Now if I plug in F0 to the capital F, okay, what happens to the Tij? If I plug in the F0 to the capital F, the sigma ij will be equal to 0 because it's a perfect balance. The same thing with the qk. So the sigma ij goes out, the qk goes out, okay, because it's perfect balance, which means I've derived the Euler equations. So what did Hilbert see? He was very happy. So he did his, of course I didn't speak to him about it, but I'm guessing he was very happy. Okay. So Hilbert plugs in, okay, and he sees he truncates after the first term in the expansion, and he gets the Euler equations. Yeah. He gets so excited, he then continues the procedure and tries to compute F1. Well, F1 is messy. So what does Hilbert do? Okay. He writes an equation for F1, but because the F1 will depend on the nature of Q, now the Q really enters the story, because if you plug in, right, at the next level you'll get ddt of some F1 stuff, and then here it'll be in, let's see if I did that right. So the first thing you'll get, let's see, no, vice versa. We'll get, say, let's do it here. I had it right the first time. So if we plug in, what's the order epsilon term? We'll get an epsilon times the F0, and then the first term in the expansion here will be the Fouché derivative of Q evaluated F0 times F1. Okay. So F1 enters as an unknown with the operator Q. But that's an integral equation. What does Hilbert do? Hilbert invents the theory of integral equations. Smart guy. He's real applied mathematics. So Hilbert, at the second level, order epsilon, invents the theory of integral equations. Okay, not everybody can do this. You're doing a problem and you invent a whole theory, okay, which plays a major role in mathematics just because you had to solve the next equation. Hilbert proves he can solve for F1. Of course, if you can solve for F1, you can solve for F2. So the sequential solvability is possible. That's the good news. Okay? The bad news is he doesn't know what F1 is. So it's a typical mathematics result. I have existence uniqueness, but the actual answer, I don't know. Okay, so this is where Hilbert stops. But let's think about what Hilbert has observed. Hilbert has observed that if I start with the Boltzmann equation, rescale to look at the macroscopic level, let epsilon go to 0 formally, which means I'm only going to see the Maxwellian distribution, then I'm going to derive the Euler equations. Hilbert does this. He knows it's formally works, so he writes and then states in his 1900 address at the International Congress of Mathematicians, this is a good problem. Formally it works. We don't need continuum mechanics. We can go from the microscopic, so Boltzmann level to the continuum level just by pure thought, no experiments involved. Okay? And that's what motivated Hilbert to propose this sixth problem. Okay? But he couldn't even get practically past the first term. Okay, so let's continue the story. I now have to erase a piece here. So let's continue here. I guess we don't. If I need this, I'm in trouble, but let's hope not. Okay. Now, with the Hilbert expansion was made sense as an asymptotic formula, but it wasn't leading to anything useful after the first term. Okay, theory of integral equations was nice, but let's think about it. Okay, if we had written, let's just stop at the first term, and we observe what's the first term. The first term, as I said, was the Maxwellian distribution, okay, which led us, and maybe there should have been a row here, I'm not sure. But, so it leads us to the Maxwellian distribution, okay, and everything here depends on the macroscopic variables. That is V, temperature, and maybe I left out the row someplace. Probably I left out the row. So it only depends on macroscopic variables. So we could have thought that F0 only depends on x and t through the macroscopic variables. So let's make a remark. Okay. F0 depends. The psi you can't do anything about. But the xt, on xt via, so it's, okay, I depend on xt, but only through the intermediary guy. It's the friend of my friend. I can only talk to my friend through the macroscopic variables, rho, theta, and v. Okay. Now that's very nice, because the equations should be only depending on rho v I. Let's call these macroscopic guys capital M for macroscopic. Okay, so this is a great note. Then you see, okay, so the mistake of Hilbert is he should have assumed, if there was a mistake, that all the terms in the series only depend on xt through the macroscopic variables. That way we're guaranteed when we do the iteration to only depend on macroscopic variables. So we assume that all the fi in the Hilbert expansion depend on the M and its space derivatives. So the only way any fi can depend on x and t is through rho theta vi and derivatives with respect to x. One derivative, two derivatives, etc. Okay. So this idea was not Hilbert's. This was the idea of Chapman and Enskog. So let's write it down. So it says take the f psi xt and we write it as f0 psi m and then epsilon f1 psi and then m plus derivatives of m. Okay? In fact, one derivative of m, etc. So that's the Chapman-Enskog expansion. What's the power of the Chapman-Enskog? Yeah.
I don't understand what fi also depends on n.
It depends on. Okay, let's go back here. Okay. Let's do f0. Okay. Okay, f0. So the next one, f1. How can it depend on x and t? Hilbert said, just assume it depends on xt, no special way. But we assume it depends on xt only via rho, that it has to be a function of rho xt, theta xt, and the vi xt, and maybe space derivatives, not time derivatives. So the only way it depends on xt is through the intermediation of the macroscopic guys.
Is that an assumption? Or
That's just a guess. Okay? Chapman and Enskog were not mathematicians, they were physicists. Okay? Because they knew what they wanted. They wanted continuum mechanics, and they were trying to see the first correction.
Basically, system is in some sense autonomous.
Yeah, yeah. It's could think of course, yeah, exactly. Autonomous in the, because you've made the dependence only on the dependent variables. Very good way of thinking of it. Okay, so Chapman and Enskog do this expansion. Okay, I thought about 1910 plus or minus epsilon. Okay, and the Chapman and Enskog, which I'll do it, but not for the full guy. It takes, okay. And now they can compute F1. That's very nice. Unlike Hilbert, who got proved existence uniqueness but didn't know F1, Chapman and Enskog, in this formulation, can compute F1. They take the F1, okay, they plug it in. Now they can compute the new correction to the Euler equations. Now they're able to rigorously compute they can compute formally, shouldn't say rigorously, according to the formulas, they compute the correction to the Euler equation, and what do they get? Okay, they get Navier-Stokes Fourier. Now the people are very excited because independent of continuum mechanics, the Navier-Stokes Fourier theory has been derived from pure rational thought, no experiment. Even better, as Carlo Cercignani points out in his book, the coefficients you get for the viscous and heat conduction terms have the right form as observed in the laboratory. So not only it's the true greatest achievement, one might say, of kinetic theory of gases. Not only do we get the Euler equations for an ideal gas, okay, Maxwell knew that, but the kinetic theory, the dynamic theory, produces Navier-Stokes Fourier, and not just, oh, it's sort of a gradient of theta or a gradient of velocity. No, it gets the coefficients right. It matches the experiment. So it's fantastic. We've gotten the experimental results. Okay, so now we have Chapman-Enskog, and it's produced Navier-Stokes Fourier. Now, there's 2 points. Okay. Does this prove that Navier-Stokes Fourier is true? Well, sort of. Okay. As long as the scaling makes sense. That is, the next term is smaller than the previous term. Okay, they haven't lost anything. So under that scaling, okay, it sort of makes sense. What else? Oh yeah, okay. Now mathematicians are, of course, if things worked in the 0th case, that is stopping at order 1, and if we stopped at order epsilon, things were even better. The next thing is, why not go to order epsilon squared? So this is order epsilon truncation of the Chapman-Enskog expansion. Notice no moments were involved here. We'll get back to the moments soon. Okay. So if we go to order epsilon squared, I mean, of course, why not? It just takes more paper. In fact, it took a lot of paper. Okay, but a guy did it. And he was, in those days, so Burnett. So Burnett published the paper. Burnett was living in South Africa, which at the time was, okay, it was originally settled by the, remember the story, it was settled by the Dutch fought the English won, so it was an English colony. And Burnett was there, I think, in Cape Town. And Burnett worked it out. Okay, so he worked out the theory to order epsilon squared. It takes pages even to write down all the terms, but he worked it out. So at the next level, we have the Burnett equations. And if you're really some people have worked out some of the terms at the next order epsilon cubes level, and okay, that's just called super Burnett, and then super Burnett, etc. Okay, so if you believe that the same logic, okay, let's be logical. Mathematicians are supposed to be logical. I must admit my own prejudice here. Mathematicians being supposed to be logical people, but on this subject they're completely illogical. So let's be logical. What if you believed Hilbert, okay, that at order 1 we got Euler. That was good. At order epsilon we got Navier-Stokes Fourier. That was even better. So we would think that at order epsilon squared we get Burnett should be even better than Navier-Stokes Fourier. But when you try to check the equilibrium of a gas, okay, no velocity, just sitting around, the gas is not moving, you perturb it a little, do linear stability theory, you plug in e to the lambda t, and you look at the spectrum, and what do you see? The Burnett equations give the gas equilibrium as being unstable, completely ridiculous, okay, unphysical. So there's something fishy in the whole story here. Okay, so If Navier-Stokes were good, Burnett should be better, but it's not better. So it calls into question the whole process here of what does it mean to carry things out to a higher order expansion. Okay, and this was done by my friend Sasha Bobolev. It's actually Alexander Bobolev. Okay, and he did it when he was still living in Russia. Now he lives in Sweden. Okay, so there's something fishy in the whole procedure. It seemed to be a good idea at the time. Now, I must admit, I picked up the chemical engineering books. So what do the engineering books say? Okay, it's a very, but the usual story of, more or less as I interpret the engineering books, they say, okay, if Euler was good, you go out one term, Navier-Stokes was better, and Burnett is bad. So it tells you, you have to stop at order epsilon. That, to me, is nonsense. How do you know where to stop? Okay, makes no sense mathematically. Now, based on experience, they like these equations, so it's sort of reasoning by reverse. I like these equations, so I know not to use this one. Well, if that's the case, then why did you go through the procedure anyways? It's not a validation of the procedure. So the point is, and we'll get to it next time, so where should you stop? Okay, to order one. If you're going to go through this procedure, why do the procedure? Again, because we're better at just common sense. We're better at solving PDEs than integral equations. And the whole idea is to change the Boltzmann equation, which is hard to solve, into a sequence of PDEs, gas dynamics-like equations. Okay, so question is where to stop. And maybe that's getting close to where I should stop, because it's a good natural stopping point. Okay, so we're going along. 1 epsilon, okay? So the answer, of course, is if there's no natural place to stop, if you're running along and there's no natural place to stop, what do? You keep running, right? So the answer is where to stop, and the answer is you don't. That's the point of this story. Okay. Don't stop. The only thing that makes sense, logically, is not to stop at all. That means we as mathematicians have to, if we're going to believe Hilbert or Chapman-Ensgog, okay, we have a series. Where is all the information in a series? Everybody teaches calculus or took calculus. We learn summation of series an to the n, summation an. Where is all the information in a series? Is it in the first term, or is it in the end of the series? And of course, the convergence of a series is based on the tail, not the first term. So it makes no sense to stop at the first term. Well, who would stop at the first term? Okay, so we need to stop. No, never. You don't stop. That is, we sum the series. So the goal is, which is the new twist to this whole subject, and I've led you through, is, okay, we've developed way to change PDEs, the Euler equations, to PDEs. One was by moments and doing moment closure. The other way is by Chapman-Ensgog, okay, and truncation. What's the thing that we should be doing is we should be doing Chapman-Ensgog. There's nothing wrong with Chapman-Ensgog. The mistake is the truncation. So what should we do? We should sum all the terms in the Chapman-Ensgog expansion. So ideally, we should write down the Chapman-Ensgog expansion, which I wrote over here someplace, I don't know. Okay. Plug it all in and add up all those terms, and change the Boltzmann equation to some sort of PDE. Now, unfortunately, nobody knows how to do that. Okay. Then next thing is, and I suggested as an open problem, okay, since nuclear engineers and other people, let's treat the linear Boltzmann equation. Then it's a little easier problem where you at least avoided the issues of nonlinearity. Plug in the Chapman-Enskog expansion and sum that. I think that's a doable problem. I can't do it, but I think it's doable. Okay. So what can we do? Okay, and then I'll do that next time. Okay, okay. Which I didn't do is, okay, let's go back to these moment equations which somehow approximate things. Okay, instead of stopping after 5 moments, stop after 13 moments. So we have these equations and much more. This was 5 and then 8 more equations. Okay. Let's do the Chapman-Enskog expansion on the moment equations, these 13 moment equations. So I'm combining two things. I combine the issue of using moments, because Boltzmann is too hard to work with, and Chapman and Enskog, which is clear. And let's do the Chapman-Enskog expansion, at least for this moment equations, and see what we get. And the miracle is, for the Chapman-Enskog expansion for the moment equations, at least linearized, you can sum up the series. No truncation. So there are no missing terms, and we understand exactly what's going on. And it's by examining the sum of the Chapman-Enskog expansion for the moment equations, we can see why I think more than likely Hilbert's program will fail. Okay? So that's advertised as a good place to go next week. And I've asked Professor Young-Jung Kim, I wrote a paper on this, and it was just published today, at least electronically, and it's now on the web, and you can have it. You pay him a few dollars, he'll do it. No, it's for free just go to the website, and anybody can have it. Also, next time I'll use slides, and instead of people, again, taking notes, I can post the slides on the website also, so you don't have to do any of the computations. And so that's a good place to stop. The bottom line is no truncations, at least in the Chapman-Enskog. Okay, good place to stop? Okay.